Hello oceanography students, and welcome to the final lecture video on plate tectonics. In this video we're going to learn about the Wilson cycle, the formation of mountains and islands, and evidence for plate tectonics. And there are some additional videos that if you hadn't already watched them, they should be helpful for you to understand plate tectonics. So make sure you do watch the additional videos, not just the lecture videos. Okay, so we're going to start out by talking about the Wilson cycle. So the Wilson cycle is basically an explanation for the formation of the ocean as well as the destruction of the ocean. So it's a cycle. The ocean forms, the ocean gets destroyed. And the Wilson cycle is put into 6 steps, 3 that are forming the ocean and 3 in the declining phase of the ocean. Okay, so these images here are showing you the different stages that are defined. So the first stage is the embryonic stage, and in the embryonic stage, the main motion is uplift. So you can see here that this is basically new crust is going to form, but first the magma that is pushing from the mantle onto the lithosphere is going to cause uplift on the lithospheric plate above it. Next is the juvenile stage, and in this stage it's a little farther along. So now the lithospheric plate has cracked because of the pressure put on it from the mantle material bubbling up and coming in between it. And it has gotten to the point where it has had the new material that's being created, the new crust that's being created is pushing the old crust away. So now what you're left with is an indent, which you can eventually have water filling in. And I'm going to show you some examples of this in a second. Then the next stage is called the mature stage, and this is where now you've had a long enough time that the mantle material has been creating new oceanic crust, and now we have defined features of a mature ocean. We have a defined mid-ocean ridge, and we have a defined continental shelf. The next stage is where we start to see the ocean get smaller. So in the declining stage, there is somewhere in the ocean where you have subduction of oceanic crust and destruction of that oceanic crust. So once you get to the declining stage, you should expect to find either islands or a volcanic chain on the continent, something in addition to trenches or other various geological features that are indicative of a convergence zone. Okay. Now, the next stage is called the terminal stage. In this stage, there is no longer a mid-ocean ridge. There's no longer seafloor spreading at all in the ocean. And instead, it's just getting smaller and smaller, and it tends to be irregularly shaped because of the way that convergence is happening. And finally, the continents suture together, and there's no longer an ocean there. And so that final stage is the suturing stage. Okay, so an example of the embryonic stage of ocean formation is found in eastern Africa. So you can see here, this is where we're looking. We're looking just south of the Red Sea along the eastern side of the continent of Africa. So what we have here is called the East Africa Rift Valley. And the East Africa Rift Valley has uplift going on, and it has the continental crust is cracking, and so you end up having a rift valley that is created there. The next stage is the juvenile stage, and examples of that are seen in the Red Sea. So just going a little bit north from that East Africa Rift Valley, you have the Red Sea. The Red Sea, as you can see, if you look along the shorelines, they match up perfectly. So the juvenile stage has linear seas. So linear sea is a sea where you have perfectly matching up coastlines on either side. So there's not a defined continental shelf yet. And another example is seen in the Sea of Cortez here where again, you've got a divergent zone basically creating a linear sea. And then the mature ocean example is the Atlantic Ocean. So the Atlantic Ocean has a very defined mid-ocean ridge, and it also has defined continental shelves along the edges. So if you were to match up the continents on either side of the ocean, they wouldn't match up perfectly on land, but if you went underwater to the continental shelf break, you could match up the continents really, really well. That's showing that they used to be attached, and because of the formation of new oceanic crust, that pushed those continents away from each other. Next, an example of a declining ocean is the Pacific Ocean. So the Pacific Ocean does still have a spreading zone here, the East Pacific Rise, and then but over here, we've got all of this convergence going on. We also have convergence along the South American coastline. We have convergence along the North American coastline. So clearly the Pacific Ocean is shrinking. It is getting smaller because of all of those convergence zones. The terminal sea example is the Mediterranean Sea. So you can see it's very irregularly shaped. There are volcanoes within here, basically due to the convergence. And the Mediterranean Sea is shrinking and getting smaller. Now, once you get to the final stage of suturing, you no longer have an ocean there anymore. The Himalayas are a good example of this, where you had, I'm going to show you in a second, another image, where you had the Indian plate colliding with the Eurasian plate. There used to be an ocean in between them. But they have sutured together, and because they have continued to press against each other, you have the Himalayas, which are a non-volcanic mountain chain. So I wanted to show you here in this image, this is the late Cretaceous period, 69.4 million years ago. And notice you have this island here. That was India. So over time, India moved to the north and crashed into this continent here and shrunk the sea that was in between it. Okay, so plate tectonics is responsible for mountains that are found on continents, so volcanic and non-volcanic. They're responsible for islands, and it's responsible for earthquakes. When I say mountains, I usually use the term mountain to describe mountains that are on continents rather than mountains that are on islands, okay? Because islands, for the most part, will usually have mountains on them. There are a variety of different types of islands, but when we're thinking about plate tectonics, we're usually thinking of volcanic islands. Okay, so let's start with how are mountains formed. So one way that mountains can form is by continent-continent convergence, as we just looked at with the Himalayas, right? So they're non-volcanic because you have continental crust pushing on continental crust. Again, neither one is subducted into the mantle to the point where it's going to melt and cause mantle material to rise up, forming volcanic mountains. In comparison, continent-ocean convergence, because that's oceanic crust going down below the continental crust, it does melt, and that does create a chain of volcanoes. So we can see that here along the western United States, and also Canada up here, where you have a chain of volcanic mountains due to the subduction of the oceanic plate underneath the continental plate. And then, as we learned in the previous video, an additional way that mountains can form is by way of transform faults, where the continental crust is kind of being squeezed together. And an example of that is Mount Diablo. Okay, what about islands? How are islands formed? So there's three ways that we're going to discuss how islands are formed. One we learned about previously was convergence between two oceanic basins. So that's convergence between two oceanic crusts. One is older, so it's going to be subducting down below the newer one. It melts, and that material rises up, causing basically a row of islands that you can call an island arc, and that island arc is going to be in line with the trench, because the trench basically signifies the location where the convergence is occurring. Another way is by way of divergence, actually. So with divergence, you can have rocks that are piling up and piling up and piling up. And when I say rocks, it's basically, oceanic crust. If it's spreading slowly enough, those rocks can pile up taller and taller and taller until they're actually above the surface of the ocean, and you have an island that gets created in that way. An example of that is Iceland. And a third way, which we haven't discussed yet, is hotspots. So a hotspot is kind of an anomalous plume of mantle material that comes up into the lithosphere, and that can be oceanic, or it can also be continental lithosphere as well, or continental crust or oceanic crust. And what happens is the plume stays in the same spot, but because the crust above it is moving, each time that moves, you have a new island that forms if you're in the ocean. So let me show you a little animation to help you see that. So here you have the mantle plume, and as it does, it creates these islands. And as the islands move away, they eventually succumb to erosion due to wave activity, because they're no longer over the plume. They're no longer growing because of that. Therefore, the erosion tends to take over and they shrink. So an example of islands created by way of hotspots are the Hawaiian Islands. So here you can see the ages of the Hawaiian Islands, The Hawaiian Islands that are farther to the west are older and also smaller than the islands that are farther to the east. And the reason why is because the mantle plume is under the big island of Hawaii. That's why it is the big island, because it is continuing to grow and at a faster rate than erosion can occur, whereas these islands over here on the west are having erosion due to wave activity overtake them, and so they're shrinking. Earthquakes can also form due to plate tectonics. So any place where you have two plates that are interacting with one another, you can have an earthquake form. So earthquakes can form at divergent zones or boundaries, convergent zones, or transform faults. And the characteristics of the earthquakes are going to be different depending on where they're forming. So earthquakes that are formed around divergent zones tend to be shallow and low intensity, but it depends on the spreading rate, with slower spreading areas having more energy release, so higher magnitude earthquakes for places where you have very slow spreading, but they're still low intensity as compared to ones that usually occur around convergent zones or even transform faults. So around convergent zones, you end up with deep earthquakes that can be felt even farther away, and they tend to be very high intensity as well. This is because there's a lot of force in between the plates, and when it releases, that's what a big earthquake is. And around transform faults, they are high intensity, but they're shallow, so they aren't felt as far as a earthquake that occurs around a convergent zone. Okay, so in the Bay Area, we have a main fault, a major fault, I guess I should say, the San Andreas Fault, that runs through, basically runs through San Francisco. And if you look at everything to the western side of the fault, it's all moving to the northwest, and everything that's on the eastern side of the fault is moving to the southeast. So eventually San Francisco will be farther north. So it's predicted, we have a major fault line, we have some smaller fault lines that are coming off of that, and back in August 2016 is the most recent prediction I could find. Scientists predict that the probability of a magnitude 6.7 earthquake hitting the San Francisco Bay Area by the year 2043 is 72%. So, and the region that they're discussing is from Healdsburg in the north to Monterey in the south. So it's a pretty big area that they're considering, but that is still a big deal. A big one is the Hayward Fault, and the last major earthquake that was on the Hayward Fault was in 1868. So scientists really believe that this fault is like a ticking time bomb, or a tectonic time bomb as they like to call it, just because of how long it's been since a major earthquake occurred on it. And the coloration here is showing you the intensity of the earthquake in 1868 that was along the Hayward Fault. So the red color is extremely intense and the blue is weak. So as you can see, everywhere around there had experienced pretty strong shaking. Now, the Hayward Fault runs right through the center of Cal Stadium, so that could be interesting, if an earthquake occurs when there's a game. But they are outside. Hopefully there wouldn't be too much damage. There's a 99% chance of a 6.7 or larger earthquake occurring in all of California in the next 30 years. So it's pretty certain that in the next 30 years is going to be an earthquake somewhere in California, whether it's in the Bay Area or Southern California even. Okay, so now we're going to talk a little bit about where the theory of plate tectonics came from. So we discussed plate tectonics. You should have a pretty good understanding of plate tectonics at this point. So now let's kind of go backwards and think about, well, how did we get this theory? So the original scientists who started to propose ideas of how this could be happening was Alfred Wegener, and he was a meteorologist and a polar explorer, and he proposed the concept of continental drift, which essentially says that the continents just drift along the planet. He didn't really have a great explanation for it, but he did identify that there was a supercontinent that he named Pangaea, which means all Earth. It broke apart about 200 million years ago, and the problem with continental drift is that his explanation of it was not quite correct. So he said that movement of continents is due to the effects from the moon and the sun, and heavy continents were slung toward the equator of the spinning Earth. And he also believed that continents could just plow through the ocean. So we know that that's not true now. But so at one time, all the continents were cuddling, and we call that Pangaea. Okay, so we get rid of all of that because it wasn't quite right. And scientists continued to look into, how the continents were moving and how these different features were forming. So Harry Hess and Robert Dietz proposed seafloor spreading in 1960, saying that the seafloor develops at mid-ocean ridges and then spreads outward. That carries the continents away also, and it's powered by convection currents in the mantle. And then finally, in 1965, John Tuzo Wilson proposed the full explanation. So Earth's outer layers consist of about a dozen lithospheric plates. When heated, the asthenosphere rises, causing new plates to form, and older plates are then subducted and destroyed. Now, of course, when Wegener originally proposed continental drift, scientists are, going to push back on that, and even, all of the steps along the way after that, coming up with a theory of plate tectonics, scientists are, of course, going to look at alternatives. So why is it that we accept the theory of plate tectonics as an actual theory? Well, there's a lot of evidence for this. So evidence being things that actually support the full theory of plate tectonics, including the explanation. Here are some things that support the theory. One is that rocks and fossils are found across ocean basins, as well as mountain ranges can also be found across ocean basins. Excuse me. And how do scientists know that they're found across ocean basins is because they can look at the rock material and match it up. You can also look at magnetic anomalies along the seafloor, which we'll talk about in a little bit. You can look at the age and the thickness of sediments on the seafloor. You can look at the temperatures along the seafloor, and within the crust. Or you can also look at the patterns of where volcanoes and earthquakes occur. So the pretty simple one is that the continents kind of line up, so you can see that they kind of fit together like a puzzle. But to add to that, we also have found that rocks and fossils of the same types of animals exist across ocean basins, and those animals could not have possibly swam across, so that is indicative that those continents once were attached. Okay, and we can see here, there we have a mountain range, which is the Appalachians and the Alps. So we've got the Appalachians and the eastern side of North America, and then we've got the Alps along the western side of Europe, or Eurasia, I should say. And then we can also look at the presence of plant fossils as well. So there are these fossil ferns that we can find all in a line, including in Antarctica, where ferns don't grow currently because it's too cold. So that must have meant that Antarctica must have been someplace where it wasn't so cold, wasn't in the South Pole. We could also use Earth's magnetic field to identify places where magnetism is stronger versus or in the same direction as what we have currently. And then it alternates as you go across the seafloor. So our Earth has a magnetism to it, and it's believed that this magnetism is probably due to the iron in the core of the Earth. And we know that it's fluid, and so it can move. And so therefore, what we think of as the North Pole right now has actually been in the south previously. So it reverses. Right? If we had a reversal now, our compasses, instead of pointing north, they would point to the south. And these magnetic reversals, they happen just periodically throughout Earth's history. And when new oceanic crust forms, it locks in the magnetism of the Earth, meaning it locks in that the North Pole is in the north. And it locks in when it was in the south. Okay, so what scientists can do is they can see this pattern of reversals. So let's say we have an ocean that's forming, right? And that ocean locks in the polarity of the Earth. As more magma comes up, more oceanic crust gets formed, and that's going to lock in the polarity of the Earth as well, and that is in the reversed polarity. So say the magnetic north is actually in the south now, right? Our compasses point south. Over time, we have more and more oceanic crust forming, and we also have magnetic reversals to flip back to the normal polarity. And so in this way, you can see that there is this pattern where you've got this strip here matching up with this strip out here, this strip here matching up with this strip, and then, of course, you have new crust that's being created, and if more comes up, then you're going to separate those strips as well. So scientists could actually see that there was this pattern of reversals on one side of a mid-ocean ridge that matched up with the pattern on the other side of the mid-ocean ridge. And that told them that each one of those lines were once attached together and they formed at the same time, which is evidence for actual seafloor spreading. So this little animation is just showing you what scientists had figured out is they were basically towing a magnetometer behind their boat, and they were going from one shoreline to the other, and they started to identify these magnetic reversals and anomaly patterns along the seafloor. You can also look at the ages of sediments and the thickness of them as you go from the mid-ocean ridge towards the shoreline. So you can see that the ages of the sediment is older as you go away from the mid-ocean ridge and towards the shoreline, and the thickness of sediment also is increases as you go away from the mid-ocean ridge because that ocean crust has been there longer and therefore more sediment can accumulate there, right? Along the mid-ocean ridge, that's new oceanic crust, and therefore you're not going to have a lot of sediment accumulating there. Scientists can also see evidence for seafloor spreading based on the age of oceanic crust. So in this image, red represents young crust and blue represents very old crust. So stop for a minute and just take a look at this and try to identify what it's showing. So where is the oldest crust? Where is the youngest crust? And can you explain that? How is this evidence for plate tectonics? And you might need to pause the video if you want to sit and think about it for a little bit. I'm going to talk about it now. So the red, like I said, is the youngest crust, okay? And we can see that that is occurring at our mid-ocean ridge, which we've identified, as an underwater mountain chain. So as you go away from that mid-ocean ridge, the crust gets older and older, right? Same thing over here in the Pacific Ocean. You have the East Pacific rise. As you go farther and farther away, the oceanic crust gets older, okay? And then here we have the oldest crust in the Pacific Ocean, and what's over there is the Marianas Trench. So you have this old ocean crust getting destroyed at the Marianas Trench. So again, this is evidence for seafloor spreading. This is evidence that new oceanic crust is created at mid-ocean ridges or spreading centers, and those spreading centers push away continents and therefore cause oceans to form. You can also look at the temperatures along the seafloor, not in the water, I mean in the actual crust on the bottom. And we can see that the hotter areas are places where you have new oceanic crust forming. And of course, our explanation for that is the mantle heat coming up and hardening in the lithosphere and creating new lithosphere, creating new oceanic crust. So of course it's going to be hotter and it's going to be colder the farther away you get from that. We can also look at the patterns of where volcanoes and earthquakes occur. So for example, the Pacific Ocean is often referred to as the ring of fire because there are volcanoes and earthquakes that basically line the whole outer part of the Pacific Ocean. And again, that's indicative of there being actual convergent or divergent or transform fault boundaries there. Now, with plate tectonic theory, we can determine what our continents looked like in the past, and we can also predict what they'll look like in the future. So here, this is what Earth looked like 540 million years ago. And if you watch this green continent here, you might start to be able to identify it as we move closer to our current time. So this one is showing you 360 million years ago. This one is 240 million years ago. Here's 120 million years ago, and you probably are starting to be able to identify the continents now. Here's 120 million years ago, and here's the present. In the future, based on current spreading rates, scientists believe that the Atlantic Ocean is going to be getting bigger, and even the Indian Ocean maybe is going to be getting a little bit bigger as well. Okay, all done with the plate tectonic lecture videos. So in your weekly discussion, I would also like you to name a place on Earth that is currently experiencing continent-continent convergence. Also, name a place on Earth that is currently experiencing ocean-continent convergence. And finally, name a piece of evidence that supports the theory of plate tectonics.